Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.
This is SpaceTime Series 23, Episode 50, for broadcast on the 25th of May, 2020. Coming up on SpaceTime, scientists create a new type of atom. A new study shows the Sun is less active than most other stars, which is probably a good thing for life as we know it. And elongated blobs of molten metals causing the Earth's magnetic North Pole to move. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Physicists have created a new, never-before-seen exotic atom called Pionic Helium. Scientists with the Asakusa collaboration at the Paul Scherrer Institute near Zurich created the new atom to study the properties of a subatomic particle called a meson. The findings, reported in the journal Nature, represent the first time laser spectroscopy measurements have been made of mesons, providing new high-precision details on their properties, including a measurement of their mass 100 times more accurately than currently known. And it places new limits on possible new forces involving mesons. The Pionic atom was created out of an isotope of helium known as helium-4. On Earth, helium-4 is usually produced through the alpha decay of heavy elements. The helium-4 isotope is usually composed of 2 protons, that's the part of the atomic nucleus with a positive charge, 2 neutrons, that's the part of the atomic nucleus with no charge, and 2 electrons, which are negatively charged and are the part of the atom that goes round the nucleus. To create Pionic helium, scientists replaced one of the electrons with a high-lying energy state negatively charged pion meson. Pions are the lightest known types of mesons, which are heavy negatively charged particles composed of an up quark and an antimatter down quark. They're commonly produced in nature in high-energy collisions between subatomic particles called hadrons, in some matter-antimatter annihilation events, when some types of cosmic rays collide with matter in Earth's atmosphere, and in supernova explosions. Researchers took negatively charged pions provided through the Institute's 590 MeV ring cyclotron facility, the world's most intense source of these pions, and then focused them using a magnet into a target containing superfluid helium. Superfluids are fluids that can flow without any resistance. To confirm that these exotic atoms had indeed been created, and then to study how they absorb and resonate with light, researchers fired various frequencies of laser light at the target, and then looked for instances in which the pions made a quantum jump between different energy levels of their host atoms. And eventually the authors were able to identify a specific jump. The jump was predicted to result in the absorption of the pion by the helium nucleus and the subsequent breaking of the nucleus into a proton, a neutron, and a composite particle made up of a proton and a neutron. And the authors detected these fragments using an array of particle detectors, thereby confirming that the pions had indeed made the jump. These exotic particles usually have very short lifespans, just 26.003 nanoseconds on average. But the authors produced an atom with a lifespan over 1,000 times longer than any other atom containing a pion, thereby allowing them to study the properties of the meson, and to carry out a search for new physics beyond the standard model, the very foundation stone upon which science's understanding of the universe is based. This is SpaceTime. Still to come, a new study suggests the Sun is less active than most other stars, which is probably a really good thing for the development of life as we know it. And a new study suggests that elongated blobs of molten metals are causing Earth's magnetic North Pole to move. All that and much more still to come on SpaceTime. A A new study has found that our sun is at least 5 times less active than other similar stars, which is probably a good thing for the development of life as we know it. A report in the journal Science, based on an analysis of 369 sun-like stars, shows that solar brightness variations are extremely weak, just 0.07% compared to other stars. To the people of Earth, the sun appears to be an ever-changing star as it progresses through its 11-year solar cycle, ranging from very little if any sunspot activity during solar minimum, the area where we are now, and then gradually building up to violent eruptions of solar flares and coronal mass ejections during solar maxima. However, by cosmic standards, our sun is extraordinarily monotonous. The observations have raised questions as to whether the sun's lack of significant variation is a basic trait of this particular star, or whether the sun's simply going through an unusually quiet phase. By examining tree ring and ice core sample records for the distribution of radioactive carbon and beryllium isotopes, astronomers were able to reconstruct the amount of solar activity the sun's undergone over the past 9,000 years. And from that, they could then infer the amount of sunspot activity taking place, and consequently, variations in solar brightness. The isotope readings show the pattern of solar activity to be consistent with what we see today. But then again, just how representative can a 9,000-year snapshot of the sun's activity really be, especially when compared to its present 4.6 billion-year lifespan? Or for that matter, the roughly 12 billion years it's expected to be on the main sequence. So to find out, astronomers looked for other stars with similar characteristics to our sun. In addition to surface temperature, age and metallicity, that is, the proportion of elements heavier than hydrogen and helium in the star's composition, the authors also looked at rotational periods. You see, the speed at which a star rotates around on its own axis is a crucial variable. That's because the star's rotation contributes to the generation of its magnetic field through an internal dynamo process. And the magnetic field is the driving force of a star responsible for all fluctuations in its activity. The state of the magnetic field determines how numerous dark sunspots and bright regions on the solar surface are, and therefore how brightly the sun shines. It also determines how often the sun emits solar flares and coronal mass ejections, which can send violent eruptions of plasma and radiation into space, and if they're pointed in the right direction, towards the Earth. Luckily, a comprehensive catalogue containing the rotational periods of literally thousands of stars has been compiled over recent years by NASA's planet-hunting Kepler Space Telescope. Now, Kepler wasn't actually studying stars, it was looking for planets. But it was looking for those planets by recording brightness fluctuations in some 150,000 stars between 2009 and 2013. In some cases, those brightness fluctuations were caused by orbiting planets transiting in front of their host star. For this solar brightness study, the authors selected those stars that complete a full rotation every 20 to 30 days. That's similar to our Sun. They were further able to narrow down the sample using data from the European Space Agency's Gaia Space Telescope. In the end, the authors focused on 369 stars which resembled the Sun in a range of fundamental properties. And the exact analysis of the brightness variations in these stars revealed a very clear picture. While active and inactive phases of solar radiance fluctuated on average by just 0.07%, the other stars showed much larger variations, averaging about 5 times stronger. However, it wasn't possible to determine the rotational period of all the stars observed in the Kepler data. To do this, scientists had to find certain periodically reappearing dips in a star's light curve, which can be traced back to star spots that darken the stellar surface, rotate out of the telescope's field of view, and then reappear after a fixed period of time. But these periodic darkenings can't be detected in all stars because the signal is simply lost in all the noise of the measured data and in overlying brightness fluctuations. The authors studied more than 2,500 sun-like stars with unknown rotational periods, finding that their brightness fluctuated much less than that for the other group. Apparently, when viewed with Kepler, not even the Sun would reveal its rotational period. One of the study's authors, Ben Monte from the University of New South Wales, says the reasons for the differences in activity aren't yet clear. But it would seem that a quiet host star might be an important prerequisite for the establishment of life on any planet in that star's habitable zone.
The work we've been doing is using data from the Kepler telescope. So Kepler was a NASA mission that launched in 2009, and spent 4 years observing just one patch of the sky, kind of as big as your hand at arm's length. And it did that every 30 minutes, measuring the brightness of about 200,000 stars, because occasionally these stars have planets, and occasionally these planets are just lined up perfectly along our line of sight to where they would pass in front of the star, and we would see their shadow go across the star. So to do this, to find relatively small planets like the Earth, you need to look at a lot of stars very precisely. So we have this fabulously rich data set of the brightness of 200,000 stars at precision of about 10, 20 parts per million every 30 minutes for 4 years. And so this is useful for finding planets, but it's also really useful for broader stellar astrophysics. You can see things like star spots on the star. You don't actually image the surface of the star itself, but we can see that the star over a few weeks gets fainter and brighter again, just like our own sun does.
Yeah, I think they've been using it for astroseismology as well. So there's such a rich tapestry of data coming from Kepler.
Yeah, no, there's really broad science. There were just by chance a few supernovae in the field of view, and so there's detailed studies of kind of the initial moments of supernovae from that. But yeah, so I'm broadly, I do some work with planets around Kepler stars, but I'm also broadly interested in stellar activity. So understanding magnetic cycles, stellar rotation, star spots, and how those change over a star's life.
And the magnetic cycles are important, aren't they? Because that's how you can determine the amount of activity a star is actually outputting, what the star's doing. And that's been important for this research into looking at how the sun compares with other spectral type G-class yellow dwarf stars.
Yeah, absolutely. And we know that we're here around our sun. Is that a coincidence? Is our G-stars, is there something special about G-stars that make them more suitable places for life than other stars? Or is this just, we're here just by chance? Other stars would be equally suitable. We don't really know at this point.
Yeah, when we look at red dwarf stars, everyone loves talking about red dwarf stars and the possibility of planets in the habitable zones around those stars, because the habitable zones are so close to the star, and it's easy to sort of spot these planets orbiting around those stars. But red dwarf stars are also very violent places because of their internal structure. They have lots of stellar flares and things like that, which would irradiate the surface of any planet.
Yeah, they have lots of flares, and they last much longer. We know that stars kind of calm down in time, that in the first few 100 million years, stars are much more active than they are after that. But the period that M dwarfs are active seems to be much longer than G stars. And so not only do you have these very large flares regularly from these stars, but they go on for a much longer fraction of the planetary system's life. And so any small planets, potentially habitable, could have their atmosphere stripped away before life has a chance to form. I'm working with a student at the University of Chicago right now who's trying to characterize flare rates around M dwarfs, and one of the things we're seeing is that they're so much more extreme than other types of stars for hundreds of millions of years.
Yeah, they may last longer than the age of the universe, but that doesn't necessarily mean they're a good place to live.
Right, if they destroy all of their planet's atmospheres right away, then even if there's a habitable planet around every one of them, and M dwarfs are the most common stars, they might all just be completely barren.
When you looked at other stars like the sun, there are a whole bunch of criteria you had. Temperature, rotational rate was important, as we mentioned earlier, and also metallicity, things like that. What did you find in terms of how active they are?
Yeah, so one of the things that's interesting to us is that there are many stars that do appear more active than the sun. We've known that for a long time, but it's potentially things like metallicity or age that drive these differences. I mean, we're just looking at a different sample. And so we wanted to get kind of the cleanest sample we could find and get closest to the sun in the Kepler field. So we identified the 400 stars that are, as far as we can tell, the most sun-like, metallicities, and most importantly, rotation rates. We look at stars of known ages and we can see that they slow down in time, and their rotation rate is a very reliable proxy for age. That if you find stars that are rotating at around the same speed as the sun and they're about the same temperature as the sun, then they're about the same age as the sun. And so this is not just a sample of G stars, but a sample of roughly 4 to 5 billion-year-old G stars. And so this gives us really a unique opportunity to place the sun in context and see how its rotation compares, or how activity compares to other stars of its type and age. And we found that our sun is quite a bit quieter, that if you look at photometric variability, how much the star gets brighter and fainter over the 4 years of the Kepler mission, the sun is really boring relative to these other stars.
That might be a good thing for life, I guess.
It might be a good thing for life, yeah. There's a few factors in here. We're looking at star spots, which are correlated with flares, but aren't necessarily identical to flares in terms of the currents. But the calmer the star is, that's probably better for life, the more stable it is. It also gives us the interesting kind of flip side that it's easier to find planets around more stable stars, because there's less activity to mess up your planetary signals. And so any alien civilizations trying to find planets around other stars, our sun would be one of the easiest targets.
As you did your search, there are a lot of stars you couldn't get rotational periods for at all.
Yes, that's correct. If you were observing the sun in the Kepler filters, you would see about 1 part in 1,000 brightness variation over a month. And there are systematics in the Kepler telescope that inhibit signals much smaller than that. And so we can find fairly short timescale events that are like the size of the Earth going in front of the sun, something like 100 parts per million. But in terms of actually finding long-term signals like star spots, 1 part in 1,000 is around the limit. It would actually be fairly hard to find the sun's rotation period in Kepler data if the sun was in the Kepler field. And so we compare to the stars where we see clear rotation periods, but maybe there are other stars that are sun-like, just kind of buried in the noise there. And so we also considered the sample of stars that are sun-like without measured rotation periods. What that probably means is that they're rotating even more slowly than the sun, or just have a very small amplitude of star spot signals. And so we looked at those, and even compared to those, the sun is very calm.
Can you extrapolate anything from that in terms of what this tells us about the need for a quiet place in order for life to grow?
We can have two interpretations of our results. The first is that the sun is inherently quieter than these other sun-like stars for some mechanism that we don't really understand. We don't have a good explanation for why it should be quieter. We just see that observationally it is. And so maybe this is telling us something about the sun's magnetic field. And we do think there might be some sort of transition that happens in the magnetic fields of solar-type stars at about 5 billion years of age. And so perhaps the sun is just in this transition region and it's very quiet for that reason. That's possible. The other explanation is that perhaps the sun is in just a very quiet phase, that there's much more longer time scale of variations. We know that the sun has this 11-year cycle, but there are longer-term signatures in there. There's things like the Maunder minimum, which went on for a few decades. You see, a series of magnetic cycles that are more active than others consecutively. And so we know there is variability in the activity of the sun on decadal and century timescales. But perhaps there's tens of thousands of year-long timescales as well. We know from isotopes and radiocarbon dating that the sun's activity has been stable for about 10,000 years, but we don't really know longer than that. So if the sun is just in a boring several millennia and then becomes more active in 50,000 years, that's possible.
I take it there's been nothing in other records that would show any sort of difference in how it's affecting life on Earth over periods earlier than that 9,000-year slice that you've been able to get through your ice core and tree ring samples. So it's not like there was a sudden change. That's kind of the limitation of where we are. It's hard to look at. We don't have good proxies of stellar magnetic activity going back more than about 10,000 years. So there's one of these two scenarios. So in a scenario where the sun is actually much less active, then perhaps that is telling us something about habitability. Certainly we're here, but we don't deeply understand what goes into habitability. A quiet star is important, but how quiet do you need, we don't really know. But we're working on it. That's Ben Monte from the University of New South Wales. And this is SpaceTime. I'm Stuart Gary. Still to come, elongated blobs of molten metals causing Earth's magnetic north pole to move. And later in the science report, positive early results from Phase 1 clinical trials of a new COVID-19 vaccine. All that and more still to come on SpaceTime. New data suggests a pair of giant elongating magnetic blobs deep below the Earth's surface are causing the planet's north magnetic pole to move at an ever-increasing rate from its current position below the Canadian Arctic towards Siberia. Unlike the Earth's geographic North Pole, which is in a fixed location on the planet's spin axis, magnetic north wanders. Scientists and navigators have noticed this drift ever since magnetic north was first measured back in 1831. However, since the 1990s, this slow drift has been speeding up, going from its average historic wandering speed of no more than around 15 kilometers per year up to its present-day breakneck pace of 50 to 60 kilometers a year. This dramatic increase means the world magnetic model, which is vital for navigation, now needs to be updated more frequently. Earth's magnetic field exists because of an ocean of superheated swirling liquid iron that makes up the outer core some 300 kilometers beneath the surface. Like a spinning conductor in a dynamo, this moving molten iron creates electrical currents, which in turn generate the planet's magnetic field. And numerical models based on measurements from space, including from the European Space Agency SWARM mission, have allowed scientists to construct global maps of the magnetic field. Tracking changes in the magnetic field can tell researchers how the iron in the core is moving. Now, a report in the journal Nature Geoscience has provided more support for the idea that the position of the North Magnetic Pole is determined largely by a balance or tug-of-war between two large lobes of negative flux at the boundary between Earth's core and mantle under Canada. Scientists combined data from the SWARM satellite mission with magnetic field maps to show that a change in the circulation pattern of the flow underneath Canada has caused a patch of magnetic field at the edge of the core deep within the Earth to become stretched out. One of the study's authors, Phil Livermore from the University of Leeds, says this elongation has weakened the Canadian patch and resulted in the magnetic North Pole shifting towards Siberia. The big question now is whether the pole will ever return to Canada or whether it will continue heading south. Models of the magnetic field inside the core suggest that, at least for the next few decades, the pole will continue drifting towards Siberia. But Livermore says given that the pole's position is governed by this delicate balance between the Canadian and Siberian patches, it would only take a small adjustment of the field within the core to send the pole back to Canada. This is SpaceTime. Still to come, the science report, and positive early results from Phase 1 clinical trials of a new COVID-19 vaccine, and claims current greenhouse gas emissions could cause more frequent and longer Dust Bowl-style heat waves. All that and more still to come on SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. There have been positive early results from Phase 1 clinical trials of Moderna's new COVID-19 vaccine. Dozens of study participants were vaccinated in the trial, and 8 went on to develop neutralizing antibodies at levels reaching or exceeding those seen in people who have naturally recovered from COVID-19. Neutralizing antibodies bind to the virus, preventing it from infecting ACE2 receptors on cells. The results of the study, which was led by the National Institutes of Health, have not yet been peer-reviewed or published in a medical journal. Phase 1 clinical trials typically studies only a small number of people, focusing on whether the vaccine is safe and whether it elicits any sort of immune response. The US Food and Drug Administration has now cleared the company to begin Phase 2 trials in July. They'll involve several hundred people, and if they go well, it'll lead to a large-scale Phase 3 clinical trial, which usually involves tens of thousands of participants. And if all that continues on track, then the new vaccine could be available to the public possibly as early as January. The COVID-19 coronavirus spread from China's Wuhan wet markets in mid-November. However, attempts by China's communist government to cover up the extent of the contagion and its decision to continue allowing international travel from Wuhan, while at the same time banning travel from Wuhan to other parts of China, meant the virus has quickly spread into a global pandemic which has now infected over 5 million people, killing some 400,000 of them and costing the world more than $7 trillion in lost economy. A new study claims current greenhouse gas emissions could cause more frequent and longer Dust Bowl heat waves. The 1930s Dust Bowl drought across North America's Great Plains caused widespread crop failures and large dust storms. But a new study in the journal Nature Climate Change suggests that things could have been much worse had they been dealing with today's level of greenhouse gas emissions back then. Scientists looked at how these 1930s heat waves would have behaved if they had happened now with present-day greenhouse gas emissions, finding that the heat waves would have been almost 5 days longer in 1934 conditions, increasing to an extra 8 days for the most severe 1936 heat wave. They also found that under current emissions, these once-in-a-100-year events are more likely to occur once every 40 years. Archaeologists have discovered a rare coin from the Bar Kokhba revolt at a dig site near the Temple Mount in Jerusalem. The ancient bronze coin, dating back to the year 132, was unearthed at the William Davidson Archaeological Park in the Jewish quarter of Jerusalem's Old City between the Temple Mount and the City of David. The coin's decorated on one side with a cluster of grapes and the inscription, Year 2 of the Freedom of Israel, Jerusalem. And on the other side is a palm tree with the inscription, Return to Israel, Jerusalem. The coin is from the period of the Bar Kokhba revolt, the third attempt to try and liberate the Jewish homeland from Roman occupation 1900 years ago. Rebels deliberately minted these coins on Roman regime coins in defiance of Roman occupation. The revolt lasted around 5 years. It caused such heavy casualties among Roman forces it took 6 full Roman legions, together with auxiliaries and elements from up to 6 additional legions, to finally crush the rebels. To ensure it could never happen again, Rome banished the Jewish people from Israel, moving them to other parts of the Roman Empire, and even changing the name of their land to Syria Palestinia. Okay, admit it. Chances are you're a cyberchondriac, a person who will first go and check out good old Dr. Google when they're a bit sick, just to reassure themselves. But a new study has found that Dr. Google, a euphemism for a multitude of online self-diagnosis symptom checkers, is usually wrong. The findings are based on a new study reported in the Medical Journal of Australia, which found that an analysis of 36 leading international mobile and web-based symptom checkers, resulting in just 36% producing a correct diagnosis as a first result. Google gets an estimated 70,000 health-related searches every minute, and close to 40% of Australians have looked for online health information in order to self-treat. A new National Centre for Naturopathic Medicine has opened at the Southern Cross University's Lismore campus. The university's Vice-Chancellor, Adam Shoemaker, says the benefits of basing the centre in a region like the Northern Rivers of New South Wales means there's an established network of support from local people receptive to trying new things. Surrounded in lush subtropical rainforests, the Northern Rivers region proudly describes itself as the hippie capital of Australia, with a strong counterculture, new age and alternative lifestyle philosophy. And as you'd expect, it's also the anti-vax capital of Australia, with the nation's lowest vaccination rates, and so provides the perfect location for a National Centre for Naturopathic Medicine. Tim Mendham from Australian Skeptics says he strongly supports any scientific research, but he's concerned that research carried out at this centre might not necessarily adhere to the same high scientific standards and peer review processes one should expect from a scientific medical research facility.
There's a number of these sort of centres, some that have been tried to be set up and were sort of knocked back by the universities. Obviously, Southern Cross University is very happy to take, I think it's $10 million, and they have funding a National Centre for Naturopathic Medicine in Southern Cross University's Lismore campus, and therefore they're supposed to be doing. Research is a good thing, but sometimes you wonder about what's going to come out of this. It's very similar to the National Centre for Integrated Medicine, which is in Western Sydney University. They're doing alternative stuff, especially traditional Chinese medicine, and they've got heavy sponsorship from Chinese organisations, etc. So it's around, unfortunately. And a curious thing is that Lismore campus got closed down very early on because of virus outbreaks. That's the irony. To try to sort of give themselves some street cred, right, or some science street cred. By saying, look, we're funding this research. What it comes out with is going to be sort of very, very interesting to see if they're sort of how diligent they are. And well, I worry about it for a start because it is naturopathy and there's a lot of garbage in that naturopathy. Outside of the be healthy sort of guidance, etc., eat healthy foods, which is all right, but a lot of other stuff. I mean, naturopaths are notoriously anti-vaccination.
They've been very quiet in the last few weeks.
Yes, most of them have been. Yeah, I know. It's obviously not something to. Yeah. Well, the irony abounds with this sort of coronavirus. It put a lot of people, it dragged a lot of people into the spotlight and put a lot of others back hiding. So it's an interesting situation. A lot of people have been flipped over, if you like, on their confident views, etc. There's a lot of churches who are going around saying that they're safe from coronavirus because because the congregation is fervently religious, etc. So we'll have to see how they work out, actually. I don't think anyone's immune, whether you're religious or not.
I think the real sad thing about all this is that it's not that they could just get themselves infected or sick or something like that, but some innocent person who just happens to be walking past them could get infected or sick or worse still, die.
Yeah, I mean, the problem is about a lot of these things, whether it's a church or whether it's a naturopathy clinic or something, people get a very false sense of security, and they think I've taken a herbal remedy or whatever, however dodgy it might be, therefore I'm fine, so I go out in the community. So unfortunately, that's a recipe for disaster.
That's Tim Mindham from Australian Skeptics. And that's the show for now. SpaceTime is broadcast on Science Zone Radio by the National Science Foundation in Washington, D.C., and through both iHeartRadio and on TuneIn Radio. Or you can subscribe and download SpaceTime as a free podcast through Apple, Stitcher, Bytes.com, Pocket Casts, SoundCloud, Spotify, YouTube, Audio Boom, Podbeam, Android, Castbox, from SpaceTimeWithStuartGary.com, or from your favorite download podcast provider. You can help support the show and the work we do by visiting the SpaceTime online shop and grabbing yourself a few goodies, or by becoming a SpaceTime patron, which gives you access to commercial-free double-episode versions of the show, as well as bonus audio content and other rewards. Just go to our Patreon page through SpaceTimeWithStuartGary.com for all the details. If you want more SpaceTime, check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, at SpaceTime with Stuart Gary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to www.facebook.com/SpaceTime with Stuart Gary. SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.
Wells Fargo presents one of the surest ways to grow your money. A Wells Fargo CD account, where you can earn a 5.00% annual percentage yield on an 11-month term with a minimum opening deposit of $5,000. Visit a Wells Fargo branch or wellsfargo.com/CD rates to open a CD account and start growing your savings with us.
Wells Fargo Bank, N.A., member FDIC.